Okay, the start of lesson 3.4 is basically shows why what we did in 3.3 is useful. So what we did in 3.3 was we graphed a system of inequalities, came up with this shaded region that worked for both, did what I called some power shading. Well, now we're going to work our way towards showing how the system of inequalities can actually relate to a real life problem. And then once we graph that system of inequalities, we're going to identify the vertices of the region that's bounded. And when I talk about the region, it's called the feasible region. So everything that you graphed in 3.3 that was power shaded, that is your feasible region. And where that graph changes direction at those corners there, those are the vertices that we're going to need to actually mark down and plug into some objective function. An objective function, what's your objective? It's basically your goal. So we're going to be talking about word problems next in our next lesson that show that, hey, maybe your goal is to make money, to profit. So then you'll write a profit function. And then after you write this profit function, you're going to figure out, all right, what are some constraints? What are some things that keep holding you back from making an unlimited amount of money? Maybe I'm going to sell some objects. I can't make an unlimited amount of those objects because maybe I don't have the storage space. Maybe I don't have the money to make the objects. Maybe I don't have the employees. There's things that hold us back. This whole process is called optimization or linear programming. And I'm just going to show you the basics of it today so you can be ready to get into the word problems in the next video. So here I have some graphing like we did yesterday. Well, x is greater than or equal to 2. I'm going to graph that as a vertical solid line 2 to the right of the origin. Where is x greater than that? That would be everything to the right. Then I find out that x has to be less than or equal to 5. That is another vertical line. And less than tells me that now my feasible region is everything in between those two. Wherever I have green and blue, that is the feasible region. Continuing on, I have y is greater than or equal to 0. That is a solid line on the x-axis. And we want to be greater than that, so it's everything above. I don't really care about this left side because it doesn't overlap with the green. I don't really care about the right side because the left overlaps the green, no blue. On the right it overlaps with blue, no green. What I care about is where they're all overlapping. So right now I've got this unfinished rectangle basically. I've got a rectangle, this small rectangle that's got all three colors in it but doesn't have a top. Finally, I need to graph y is less than negative 2x plus 12. That has a y-intercept of 12. So that would be, kind of losing my origin here. I think there's my origin. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then slope's negative 2, so we'll go down to 1 right, down to 1 right. I'm going to do this a bunch of times because what I need to be able to identify is where our boundary lines cross. And then now that one would be dotted. And where is y smaller? That would be down. The main thing to note here is when I go down, this is the region that gets colored. There's a small trapezoid right here that represents our feasible region. Okay, that small trapezoid then has 4 vertices, and we need to be able to identify those vertices. One of the vertices is at 2, 0. Another one is at 5, 0. Another one's at 5, 2. And then finally there's another one up here at 2, 8. Important that when you do this you're using a ruler, and I like to put as many dots as possible using the slope so that it's a lot easier to see where the lines cross. Otherwise you could solve a system of the equations here like we've done with elimination, substitution if it's hard to determine where they cross, or maybe they cross at a fraction where you could use your graphing calculator in that intersect function. So now all we do is plug in these numbers, these vertices, into the objective function. So I'm going to plug in 2, 0. That would give me negative 2 plus 3 times 0. That would be negative 2. I'm going to plug in 5, 0. That would give me negative 5 plus 3 times 0. That would be negative 5. I'm going to plug in 5, 2. That would be negative 5 plus 3 times 2. That would be 1. And finally, plug in 2, 8. That would give me negative 2 plus 3 times 8, and that would be 22. Now, when our region is bounded, and when it makes a polygon, like I said, it was a trapezoid, you get what's called both a minimum and a maximum. This one has a minimum of negative 5. That's the smallest number. And that occurs at 5, 0. It has a maximum of, what's the biggest number? 22. And that occurs at 2, 8. Every other number that I pick is going to be between negative 5 and 22. So if I pick any other dot in this feasible region and identify the x, y, and I plug it into this, negative x plus 3y, my answers are going to be between negative 5 and 22. What happens if you don't get, excuse me, I got to erase this here, clear ink. What happens if you don't get a bounded region or a polygon? Well, this is an example of that. First, I'm graphing x is greater than or equal to 0, solid to the right. Now I'm going to graph y is less than or equal to 2x plus 2. That would be a y-intercept of 2 and a slope of 2, so it would go up 2, 1 right, up 2, 1 right. It's going to be a solid line. And where is y smaller? Down here. Again, I'm really only interested in where they overlap. So right now I'm only shading where it was already blue. And this last one, kind of in standard form, this is what it would look like in standard form. So the intercepts are 5, 0, and 0, 5. So I've graphed that using the intercepts. In order to go from up 5 to over to the right 5 like this, basically the slope's negative 1. That one's a solid line as well. And now if I plug in 0, 0 here, I get 0 is less than or equal to 5. So 0, 0 is an answer. So I said if you plug in 0, 0, it works. So I'm shading towards 0, 0. So I'm only going to shade where it's both red and blue. And it looks like my final shading, my final feasible region is this right here. Well, this is unbounded. It goes forever and ever and ever and ever and ever and ever and ever that way. So it doesn't have a max and a min. It only has one or the other. The process for identifying that is the same. The same beginning. You identify your vertices, which look like they're at 0, 2, and 1, 4. So I have vertices at 0, 2, 1, 4. And now I plug those into my objective function, which in this case was x plus 5y. And when I plug in 0, 2, I would get 0 plus 5 times 2 is 10. And if I plug in 1, 4, I get 1 plus 5 times 4 is 21. Now what this means is that either 10 is the smallest number I can get or 21 is the biggest. I'm not sure yet, but I know that's the case. Either 10 is the smallest overall value I can get or 21 is the biggest. If you want to figure out which one's which, just pick any other point in the feasible region. I don't know, let's use 2, negative 4 for just because I felt like it. Just has to be in the feasible region. I'd advise you to get away from your vertices, get a little bit farther away, so that's why I went down there. So if I plug in 2, negative 4, that's going to give me 2 plus 5 times negative 4. That gives me negative 18. And that shows me right there that 10 can't be a minimum. So 10 can't be a minimum, therefore 21 is a max, and it happens at 1, 4. Okay, this last one I cover in this video is all set up, ready to go. The graph is done. It's not shaded. The intent was to have it shaded in here. So then we're identifying the vertices. There's 4 of them, right here, 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 here. The vertices are at -3, 1, -5, 4, 3, 0, and finally it looks like 4, 6. 4, 6, just double check. Yeah, okay. So we're going to plug those in. One's going to be a max, one's going to be a min because it's bounded. Now I would challenge you at this point to press pause and see if you can get the right answer or not. Come back, see how you did. Alright, if you press pause, here we are again. Here's how it should have went. I want to plug in 4y minus 3x. Hopefully you didn't get fooled. If you're plugging in -3, 1, it goes 4 times 1 minus 3 times -3, because actually 1 is y. I got the y first. So that would be 4 plus 9, 13. Now if I plug in -5, 4, that would be 4 times 4 minus 3 times -5. That would give me 31. Plug in 3, 0. That'd be 4 times 3 minus 3 times 0. That would be 12. And when I plug in 4, 6, I get 4 times 6 minus 3 times 4. 24 minus 12 is 12. Now, I accidentally plugged in an x for a y, so I need to go back. Okay, well, I'm going, wait a minute here. I don't think I'm supposed to have 12, 12, so now upon further review, look, I got fooled. I put 4 times 3 right here, so this is, be careful, it happens to the best of us. So I put 4 times 3, I got carried away. It should have been 4 times 0. And then minus 3 times 3, so that should have been -9. Okay? So sorry about that, but just to show you, hey, it didn't even happen to me. Now I've got a bounded region, so I have a max and a min. There's my maximum. And there's my minimum. And again, you would tell me there's a max of 31 at -5, 4, and a minimum -9 at 3, 0. Any point that I pick that's in this shaded region will give us a value when you plug it into the objective function between -9 and 31. I'll work on the word problems on the next video. Thanks for watching. Have a great day.